Before the seminar starts, we're going to show you how to navigate through the video. Below the YouTube video is the Show More button. Click the Show More button to reveal the index. You can skip to the point that you want in the video by clicking the blue time link.
Right, welcome back. So we're looking at research, and here's number 2. Best practice links algebra skills to number skills. It's not always obvious to students that what you do in algebra is like generalized arithmetic. And I think you would definitely agree calculators have a role. You know, if I'm going to be dealing with algebraic fractions, should I introduce the calculator for numeric fractions? Might be a bad idea. There's a really good researcher called Malcolm Swan. And Malcolm Swan says, as maths teachers, we should try and generalize as much as possible and as early as possible. I was thinking about that question we had first thing. Do you remember it? It was the tricky part of question 1. Is there any way you can get generalization into it? You know, if you have a good student and they do it no problem, can I generalize in any way? Okay, so I could fit x in. Do they have to be the same, Pat? So do you remember this one student who put in negative 26 and plus 20? So I could put in x and y, right? 2 x's or x and y. How many answers are there to this question? Infinite, isn't it? There's infinite possibilities. But the beauty of algebra, you can talk about how numbers behave when you don't know what they are. So if I do have x and y in the box, I don't know what they are, but is there a relationship between them? They have to add to minus 6. So in general, the 2 boxes, x plus y equals minus 6, which captures all those infinite possibilities. So that's the power of algebra. Question, or number 3 there, I mean, I think that's fairly obvious. You're going to have issues with inequalities that are algebraic if you can't handle numeric inequalities, or you're not comfortable with working with numeric inequalities. First thing we're going to do after lunch then is have an exam, because usually I find it wakes people up. It's been very competitive so far, this exam. There's only 30 seconds in it. Okay, can you try this for me, please, and hide your answers from the people around you? Right, are you ready? Okay, here we go. Here's your questions. Right, time up. Don't show anybody. Right, Siobhan, first one, did you get an answer? Two. Okay. Anyone get an answer for question 2? 2504. What's it? 2525. And question 3. How much? 2459. Now I was deliberately playing a bit of a trick on you there. I was putting you under time pressure, which is another myth about mathematics. You know, to be good at maths, you've got to be able to do it fast, which is a whole load of nonsense. But when you force people to do things quickly, they tend to make mistakes. Like some of the top mathematicians in the world, they reckon, are really, really slow thinkers, really, really slow workers. I don't know if you've ever noticed at parent-teacher meetings. Did you ever hear stuff like, his dad has a way to do it, and it's faster than yours. Can he use it? You know, as if fast is necessarily good. Phil, you're looking perplexed at those answers. Are you happy with them? Okay, neither am I. But the point here is linking number in algebra isn't always done explicitly by students. So is there any way I can get algebraic reasoning into this? Where are those numbers?
Squares.
Right, they are squares geometrically, but where are the numbers that we're squaring? Position-wise, roughly, they're all in and around 50. What do numbers that are in and around 50 look like? 50 plus something. How many numbers does that describe? Infinite. So you're capturing them succinctly here with this little expression 50 plus x, but that's all the numbers in and around 50, and here's what we're doing with them, we're squaring them. Let's look at the general case. What's the answer to this? 2,500 plus 100x plus x squared. So what's that? That's what happens when you square numbers that are around 50. Take the first case. If it's 52, what's my x value? 2. So question 1, if x is 2, 2,500, 2,700, 2,704. Our first answer. What about the second case? X is 5. 2,500 plus 500 plus 25. So question 2, answer 3,025. Okay, third one, slight little catch. X negative, it's minus 3. So we have 2,500 minus, if x is 3, or negative 3, minus 300 plus 9. So my third answer has solution 2,209. Now I don't care about the answers because I was trying to force you to do it quickly. Forget the answers. Can you see the point that when students meet algebra, they don't typically see it as generalized number? You know, they don't see it as applicable to number. So I want to tell you a little story here about one of them. And this is true, and you can check it out. I had a teacher at a workshop who said, I went into a pub and I sat next to this old guy and he said to me, what do you do? And I said, I teach maths. And the guy said to him, well, do you know what? There's a really fast way to square numbers that end in 5. So this is what the old guy in the pub said. Any number that ends in 5, when you square it, the number ends in 25. And to get the beginning of the number, so we'll use our example, let's say 55 squared. To get the beginning of the number, take this, square it, you get 25, and add 5. That gives you 30. There's your solution. So tell me about 95 squared. What does it end in? 25. Square this, you get 81, and add 9, you get 90. So it's 9025. What about 145 squared? Square it, you get 25, or ends in 25, square that, you get 196, and add 14 to 196, I get 210. So 145 squared quickly is 21,025. That's the solution. But of course, the best question that you can ever ask in a mathematics lesson. So I'm throwing that back over to you now. There's a trick in number, but the algebra will explain it. Can you try and work out why that happens? And show it to me symbolically. Like our problem here when we're trying to generalize is, what do all numbers that end in 5 look like? Any number that ends in 5. They share a common property. What's it? Okay, so what's n for this one then? Okay. The previous one, n would be 1. 10 take 5. So let's think about that. 10n take 5. If I square that, I'll get 100n squared minus 100n plus 25. It doesn't have what the trick is giving me though.
Yeah.
Do you know, so can you make a slight change to it?
When you square it, you're getting 100n squared, you're moving the number along 2 columns.
Yes, it's the middle term is the problem though. The middle term is negative 100n.
If you just write it as a plus 5 squared, you get a squared plus 10a plus 5. And multiply.
Problem with a plus 5 squared is what if a is 7? Can you see that that's going to be 12 squared? Now you're just at the cusp of it. Like, I'll ask a question here to see can I get you there. Think of the numbers that are not the digit 5 and what they represent. Like, what's that 13 represent? 13 what? That 13 is 130, isn't it? The number that's not the 5 are multiples of 10. That's 13 tens and a 5. 7 tens and a 5. That's 240 tens and a 5. So what's any number that ends in 5? 10n plus 5. And then if I square this one, what do you get? 100n squared plus 100n plus 25, right? So that takes care of the plus 25, doesn't it? Every single time. That's any number ends in 5 forever. And look at this part. Can you take anything out that might explain the trick? You could take out 100n, but what about if I just take out 100? So there's the ending in 25. There's the squaring the number and adding it to itself. And what's the reason that's there? Because it's moving the decimal places, its place value. Think about our example. 55 squared is 3025. What does that 30 represent? That's 30 hundredths, which is where our 100 comes in. And, you know, there's the algebra describing how the numbers are behaving, no matter what the numbers are. So that's useful to be able to generalize quickly about number using algebra. Okay, number 3. Teach the skills in different ways to reach a variety of learners. So, do you remember this array model we were talking about? Remember drawing your grid? The advice we have is to start in number with it, not just drop it into algebra. But Mairead mentioned there this morning about long division, and I'd like to look at that if we could, because I think it has big advantages. So I want you to try this for me first yourself. Can you multiply those two? But you must use an array, so you must draw a picture for the product. Is there any way I know how many windows are going to be in my array grid? Yeah, it's a linear 2 by quadratic, so it's going to be 2 by 3. It's going to be 6. And I'm multiplying x take 2. I'm just going to fill them in here by x squared take 2x plus 3. Tell me what's inside then, box by box or window by window. In here? X cubed, right. Can I have x cubed anywhere else? Why not? It's the only place you have x squared and x. Good. What about down in this window down here? No, obviously in class you may have to do this. So I get, again, can I have a fixed constant anywhere else? No. So that's important in the division, isn't it? You're using it for division. Okay. What about the rest then? You can fill them in any order you like. What's in here? Plus 3x. Plus 4x. Again, if the student isn't sure, just represent the dimensions. That's negative 2, and I get plus 4x. And you know the two of those are going to combine together. And then these two are going to be your x squared terms. So I have negative 2x squared And what's down here? Negative 2x squared again. And they're going to combine. So what's our answer? It's going to start with x cubed. Then negative 4x squared plus 7x, isn't it? And then the constant is minus 6. Right, is that okay first? So a couple of things you need to take out of this for long division. These side lengths are very important, that the students see that they're congruent to each other and that they're the only places that you can get an x cubed term and a fixed constant in those windows. Now, Maria, I might bring you in here. So there's our answer. When it comes to long division then, do you remember I said this morning, daddy, mammy, sister, brother? Do you know what I mean? That's the standard algorithm for long division. Let's just chat about that for a second. Are there any flaws to this work or shown this method? What type of mistakes do you meet a lot? Signs, adding terms, even in the subtraction. Have you noticed if they make a mistake in this, they'd nearly be better off to start the whole thing again. And I wonder sometimes, are they learning much using this method? Like you can, our syllabus at second level, you don't have to use that anywhere. You can avoid that entirely. So let's have a go at trying to do it with an array. And what I want you to do here is just take a look at the example first, and then I'm going to get you to try one yourself, okay? So, Mairead, can you provide the commentary? Right, you tell me what to do.
Okay, the first thing I asked them, so root secondaries I did it, and we just finished factorising.
Okay.
So I said, if you can divide an expression by something, can you give it another name? So they said it was a factor, and then I got them to set up the box like they would have with factors, so that
Okay.
x minus 1 would be down the side, because that would be one of their factors.
Right, and do you put it here as well?
No,
Okay.
I haven't, but.
Right.
And then they put in the first term, the x cubed there, because it gives them that one. In the examples that I read up, they also put in the last one, but I didn't for the reason that I'd like them to be able to do it in fifth year.
Okay.
And you know, with the factor theorem ones where they have to get the remainder. So
Okay.
to put in the last one, it's kind of tricky to figure out
Okay.
the remainder, so I just left that blank with them.
Right.
And
So,
then they start and they would have said, okay, x minus 1 is a factor, so what do I multiply x by to get to x cubed? And they said x squared at the top. And then they have the length of the next rectangle directly below it, so they can say area of that rectangle then is x squared by minus 1, which is a minus x squared.
okay.
And then I put in a diagonal line to go from
These
there
two?
to there. Yeah.
So-
Because those two together
Must give me.
give you the next term plus 2x
Yes,
squared.
so that's going to be plus 2x squared.
So they're on their number line and they're at minus x squared. They need to get to plus 2x squared, so they need to add 3x squared. That goes in there. Now they have the area of that box. They know the width of it is x, so what they need to multiply x by to get to 3x squared, so they put in a plus 3x up there. And then they
So-
have the length of the box beneath it.
So it's almost, it's a system, like, isn't it? Yeah, so that's plus 3, that's negative 1. So in the box you've minus 3x.
Yeah, and then
And you know,
diagonal again.
aligned with this one, you get,
You should be getting minus x.
it's
there.
minus x.
So they're at minus 3x, so they need to add 2x.
Okay, so they need to add 2x.
And then they have the area.
So
of
you're
that
just,
box,
yeah, so you know that's x. So that's plus 2.
And then
So this is plus 2.
I was kind of using that as their check with them. at the
Okay,
end, So
so-
plus 2 by minus 1. If they're getting their minus 2 in there, then everything is right. And it's helping them to spot sign mistakes or things like that.
Yes. And you know, just in the middle, I'm just thinking a lot, or thinking as you were talking about that, isn't this the issue as well with the standard approach?
Yeah.
Trying to get them to add 2 terms, or what do we need to add to another term to produce this one? Something that could be useful here, and I haven't seen it anywhere in the books, but do you know when we're working with integers and we get so much use out of a number line for addition, subtraction of integers, we tend not to touch it for algebra.
I had to get them to draw a number
Yeah.
line for the first couple they did, and that really helped.
Yeah, I think it's probably, like if you think in number, isn't that the reference distance on our number line? So we say that's twice that distance. And that's the same distance, but it's in the other direction. And that's minus 2 times, if you like, that direction. What's stopping us using it for x? Just as a different way to represent gathering of terms. You know, so if I'm looking at 2x subtract 3x, it's the exact same thing as 2 subtract minus 3 with my integers. And similarly, I could have a number line underneath that had y in it with just a different length. So this is a different representation to what we saw this morning, which was the area one. Maybe I could use a number line there too. Okay, your turn. Will you have a go at this one for me? Okay, with this one, what's going to show you, you can do it in quite a few ways. So here's a different way to do it. I could say that's the first term. It's 6x cubed, and this is the constant term. It's negative 60. So I'm going to fill the constant in, right? Just to show it in a different way. What's here? That's 3x squared. And if this is plus 3, then what's that distance? That's minus 20. And even if you were just to stop there, that's 2/3 of your answer. You've really done no work to get there, you know. So take a look at what's in these two. So that's minus 40x. You know, added to that, whatever you've added to that, you've got to make the x term. So that's negative 7x. What will I need to add to it? That's plus 33x. If this is 3, then that must be 11x plus 11x. So there's my answer. 3x squared plus 11x minus 20. Mairead was using that box to decide what was right. I'm just going to use these two, just a different way. So 11x times 2x, that's 22x squared. And then down here I've got plus 3. We know that's 3x squared. It's congruent to this. So that's plus 9x squared. And if you combine those two, you get... And that is the x squared term, isn't it? So we have our answer. As I said to you this morning, the whole maths team would nearly need to be using it, because it's really not going to work if it's just you showing it. They'd want to see it, and they need to see it in number first. In a way, I've been using it for a while. I feel like the students get more out of that. There's more reasoning in it than the other one, which is blindly following an algorithm which can easily go wrong, you know. And this was, among other things, this was done back in workshop 5. So I just want to show you one last application of it in factorising. So I want to see first, has anyone seen a common mistake from students in class with this factors by grouping? So have you ever seen a student do this? B into A minus C plus D into A minus C, and stop. And not go to the extra line that we want them to get to. Now, what's going on in their heads? Why did they stop? Because, according to, I have factorised. You just asked me to factorise. I factorised the highest common factor. Whereas what do we want them to get to? B plus D is multiplied by A minus C. That doesn't exist if you use an array. So just like those questions where we tell the students you can mix them up if there's any, if you don't have something in common, you can throw the values in any way you like into this, and then just pull out what's in common. So what's in common here? This is B. If I drag out here, there's D in common. In this direction, anything in common? No. So, not going to work. Now what's the problem there? These two don't have anything in common, so I'm going to not be able to factorise something out. So what will I do? Rearrange them. And you know, I think sometimes we have to do that type of thing so that the student doesn't feel like, you know, well, the maths teacher knows how to do it all the time. You're trying to emphasise, well, try something else if that doesn't work. So let's put them in differently. And what I found in class using this, if you fill in this direction and this direction terms that are common, then you won't have a problem. So look, if I put AB here, and I put minus BC here, and I put my DA term here, then it has to work. So drag out what's in common. What's in common here? This is A in this direction, minus C. In this direction, B, and in this direction, there's a D in common. Now look at the difference. If I draw the array, I'm at the factors straight off. If you like, there's no middleman. There's no HCF factorising needed. And if you are interested in looking at other things we did, because we did quite a bit on it in Workshop 5, go to the website and look at the afternoon part of Workshop 5. Okay, and you'll see lots more examples. Right, that's number 3. Number 4, this is going to be interesting now. Do you know the way they say that trying to give up something like cocaine and trying to give up cigarettes, the cigarettes is harder. Right. This section, some of these things we're going to talk about, okay, are really difficult habits to get out of. Number 4 says, avoid informal shortcuts. I'll show you a couple of examples of what I mean first. Has anyone heard of the butterfly method for addition of fractions? I saw this recently on there's a Google group for maths teachers, and somebody put this up suggesting this is the way to add fractions together. So the method is that you draw a butterfly, and in the antenna of the butterfly you get 2 numbers, and you get 1 number in the tail, and it works every single time. And it's got the added beauty of cross multiplication embedded in it as well, which is always a good thing, isn't it, for our students? And it gets you the right answer. And you know what? It's a fantastic method for that class. You'll be able to do all those questions, the addition of fractions. What's the problem? It's going to cause havoc later. It's not connected in the brain to anything that really makes sense. So 6 months down the line, there's at least one student thinking to themselves, oh yeah, do you remember that butterfly thing? What did I do there now? What was it? And did I? So it causes all sorts of confusion. Of course, the other thing they're going to do is when you're multiplying, dividing, or subtracting fractions, they'll throw it in there too. Okay, so that's the example of an informal shortcut. Might be good in this class, but in the long run, could come back to haunt me. Or, do you remember earlier we said let A be an apple and B be a banana? Here's the question that's in the test. A is an apple, B is a banana. What's the answer to the question? Yeah, find the total cost there of 3 apples and 2 bananas. Now I want you to look at a different question for me and tell me what you think the answer is. What do you think? Right, so we have a vote for A. It's A, okay. It's B. It's C. Wow. Siobhan?
It's D because it's the cost of, however, not much fruit I buy. It's just the number of dozens and bananas.
It just says the number of bananas.
Yeah.
So 2 each.
Make sure you read this. So if the variable A is representing the number of apples I buy, then 3 times the number of apples I buy is the cost of the number of apples that I buy. And 2 multiplied by B is the cost of whatever number of bananas I buy. So the correct answer is D. Now look at, even among ourselves, you can see the point in that second question. The expression is 3A plus 2B. It's identical in both, but totally different meanings because the variable was defined differently in the 2 questions. So A is an apple and B is a banana would lead students to give you A as the answer to both questions, wouldn't it? The answers are very different. So what I want you to do now, and this will take honesty now on your part, okay? Can you think of other shortcuts that we use? And I've compiled a list since last September. So I'll tell you what people have told me. What shortcuts do we use that may not be the best idea? Right, so Annie, Dave, had you any there?
No, we're just discussing bringing the other side and change.
Yeah, that's a huge one, isn't it? Yeah, cause a lot of problems. Cross multiplication, another classic.
Dividing fractions,
Oh, yeah, turn it upside down and multiply with no reason given. Okay, what else is there?
Multiplied by -1.
When is that?
Negative x
Oh yeah, multiply by a minus across it, or change all the signs. Which is another shortcut. Change all the signs. Cancelling is a big one, isn't it? Like it's amazing the things that teachers have said to me that they see. Cancelling, that, you know, that's a teacher said. Student just writes minus down. Cancel those x's, or root 2 over 2. Of course, that's just root. But from the student's perspective, can you blame the student really if I say to them in class, cancel the 2's, and then 2 months later this appears and they do this? Because it means something different to us and to the students. To them it's a free rein to do mathematical kung fu wherever they like. You know, if the numbers are on the same page, you can cancel them. And sometimes teachers can say things that make perfect sense to the teacher but are totally mysterious to the student. Like x squared over x, you can cancel those. You know, we know why, but from the student's perspective, they're looking at it going, what's after happening there? So this subject is great, you can just cross things out wherever you meet them. The researchers have said these are the big ones. When you move across the equals, you change the sign. You've seen that? And it's interesting with students when you go in with students to see their scripts. Has anybody done that? Seen to look at Leaving Cert scripts after the exam? The mistakes are never the difficult calculus. It's always in the basics. I suppose it's human nature when people relax to make mistakes. So you will see y is 2 from that type of equation. Again, you know, this moving around the place. And students don't seem to mind if they internalise that. They'll do anything. Like, you know, this turns into, oh, that comes across, it becomes plus 7, so that's 7y. And then this comes across here and becomes minus 6. And they don't have any problem writing that down. Next one. All the letters to the left, the numbers to the right. Change all the signs. If you tell a student in maths it's okay to change all the signs, don't worry, they'll change all the signs for you and end up with the same expression on the right. And that's why we can have issues with transposition, because I've just learned tricks with equations. I had a student one time say to me, which one of those x's do you want me to get? Do you know, that's when you know you have bigger battles to fight. Which x do you want on its own? Cross multiplication, it's a virus. Difficult to get it out of a classroom if it's in there. Trouble is they'll use it everywhere, anywhere they see fractions. Cancelling, some beauties here. And have you noticed in students' work with cancelling, they'll just run with it, even when it gets ridiculous. You know, it turns into 1 equals 5. They don't have a problem writing that. Yeah, 1's the same as 5. It's a great subject. There's even a mistake in here, if you can see it. Going from this line to this one. Or if the numbers are there on the same page, do you know what? Just cross them out. Simultaneous equations. One researcher says, classes he went into, this was like learning black magic for students. Simultaneous equations. Have you ever heard a method like this one? The bottom line, multiply it by the number that's in front of x on the top with the sign changed. And the top line, multiply it by the number in front of x on the bottom without the sign changed, and add the 2 lines. And the x's will cancel as method. Now, students expected to take that on board, you know, and apply it. And have you ever noticed that these are a problem? A big problem? It takes students a while to get into that. You'll think about what sort of errors you see here. They'll square that and get x squared plus y squared, of course to do, is 64. And then subtract, and you get 0 is the same as 30. Now, it'll make you wonder, should we think about teaching some substitution at junior cert to get them into the mindset for this one? Don't know. Maybe they should see it. Right, the last one. Teach algebra as a problem-solving tool. That's what it was invented for. Will you go to your booklet there, the white one, and look at question 18 for me. This was the marker and the pencil. The people that did give this to students, how did they do? Dave, you haven't seen this question before, have you? If you were asked to answer it in an instant, what's the answer?
40 cents.
Yes, 40 cent. And that's the most common wrong answer that we got back. But you know what? We don't have to feel too bad about it, because this Daniel Kahneman in Thinking Fast and Slow, they took that question to Harvard, Stanford and Princeton first years, and they struggled big time with it. 40 cent was the most common answer. If you put some algebra onto it, let's say we define the cost of the pencil in euros as X, then what's the cost of the marker? It's X plus 1. And what's the sum of them? Is 140. And look at how fast algebra sorts out a tricky enough problem to think about. So we've got 2x plus 1 is 140. And again, if I go on and solve it in the correct manner, I get x is 20 cent rather than 40 cent. One student did something really clever with it. He or she tested every answer. You can only do multiple choice. And it was either too low or too high, and then settled on what the correct one was. So algebra, using algebra to solve problems, I suppose it's common sense in symbols. It can take something that's tricky enough and reduce it to very, very manageable work. The keynote speaker at the conference last year was this man. And what was his name? Because you were there. This was Tad Watanabe. And Tad spoke on the Friday night about different cultures and teaching of mathematics. One of the points he made was there are different levels of maths teacher. He said there's level 1, level 2 and level 3. And a characteristic of level 3 maths teacher, which are the top teachers, he said was the type of questions that they ask. So the best maths teachers ask the best questions. The other thing he mentioned was sometimes the skill is in how you use what's at your disposal. You know, he was making the point that you could give the same resource to two teachers, but they may use it in totally different ways. So he tried this with the group. So he took a look at some textbooks, and he found questions like this in our textbooks. So you know this typical first year geometry, transversals and parallel lines, and you're trying to find the size of angle x. His question wasn't to find the size of angle x. It was find the value of x in as many ways as you can. I think at the conference they got 11 or 12 solutions, which could be explained by it's a Friday night, and these are maths teachers who on a Friday night go to maths conferences. So maybe they may be better equipped to find x in 11 ways. Can we find it? Wouldn't mind if we got 11 ways. Could we find it just in 3? Because I do realise now it's the afternoon, okay? You're just entering into what's known as the post-lunch slump. Yeah. Fight your way through it. It's like the marathon run around the wall. But try and do this for me maybe in 3 or 4 different ways if you could. We'll just gather methods as we go. Has anyone got a method? Sean? Okay, how? Right, so a line parallel here, is it? Or, oh sorry, this way, is it?
I go parallel to the other.
Okay.
Take the right hand side of the top line.
This one?
Yes, draw a vertical line coming from the top
Okay.
down.
To there?
Gives me a right angle there.
Okay.
90 degrees, 60 from 90 degrees, 30 on the top. And then you've got 30 and 90. Subtract for 50 degrees. When you work with the bottom, do the same thing.
Now is the problem with the bottom, okay, it might be here,
Yeah.
that's 90, and you got that's 40, is it?
That's
It's their alternate.
40.
So job done, isn't it?
Yeah.
Without it, yeah, so I get 100 degrees is x. Right, there's a way. Give me a different way.
You just brought the transversal straight down.
Transversal straight down, so this one here like this.
Yeah.
Okay, and then
60.
this is 60.
And exterior angles.
Well done, that's the external angle or exterior angle, so x is 100 degrees.
Continue to do the transversal.
This one,
Yeah.
and that's sort of like a similar method, is
Yeah,
it?
same way.
So what are you saying, that that's 40?
Yeah,
And this is?
continue both of them and actually give a vertically opposite.
Oh, which is an interesting one. Yeah, we'll come back to it. Vertically opposite. So there's 100. And the other way? Connect a point here, right through here. This is, what's that?
It's 90.
That's 30. This is 50. But this is straight, is it? So we get 100 degrees. Did anyone see a fifth way? No, they're not directly below each other.
Parallel line through the point, and then you just have two alternate, no, through the point there.
This one?
Yeah,
Here?
yeah, and then you just have two alternate angles.
Oh, you just go that 60 directly.
Yeah.
And that's 40. Some people built a parallelogram with this and use the fact that opposite angles are equal in a parallelogram to do it that way as well. Can you see the point that he's making though? Instead of just giving the question, say find x and be satisfied with x, he's saying try to milk that question for as much as you can. So you might actually be better to aim to cover less but to get more from what you do cover. I'm going to put a question up next, and when I showed this one day, a teacher sighed as if it was a long lost relative that she was looking at. It wasn't, it was a Junior Cert 2004 maths question. So here's what they were asked in 2004 on paper 1, it's higher level. Does anybody remember teaching this? Oh, good old days. I don't want you to do it at all. I want us to just think about this as a question. We're discussing algebra as a problem-solving device. Where is algebra as the problem solver in there? Right, the perimeter is 14. The question is telling us even, well, let the width be x and write an expression in x for the length of the rectangle. My students used to find that very hard. Very commonly you would see 14 minus x was the length. Show that the area is 7x minus x squared. That could be tricky too. Then look at this part. Let f be the function 7x minus x squared. Draw the graph of f for 0 to 7. So it's almost as if in the exam question that's divorced from what came before it, you know. We're doing all this work with this rectangle and then suddenly it says let f be the function. It's dropped in. And in reality, that's what algebra is as the problem solver. It's the function that models the situation that you use to solve your problem. If you're going to boil that whole question down to one problem you're trying to solve, what is it? What are you trying to find out? And it's one of those three questions at the end, but it's the key one. What's the biggest area you can make? If you have a perimeter of 14, what's the biggest area that you can make? If you want to create mathematical problem solvers, this is too scaffolded. It's too fake. It's taking you by the hand and it's telling you what to do. It's not even linking the function to the context, if you like. So it's sort of divorced from real problem solving. So what I want you to imagine is, pull the whole thing apart. Right, take all the scaffolding out of it. And let's say it was this. It's a Mr. B. Marley, okay? And he wants to enclose a herb garden. He's growing some herbs. But he's only got 14 metres of wooden fencing. And the question is, what's the biggest possible garden that he can have? Well, it's the same question as the previous one, isn't it? But there's no scaffolding. Now, what I want you to do now is, how could you go into class with that at Junior Cert first and get the most out of it? If that's the starting point from the student's perspective, how can you go in and get the most out? Where would you want them to start and where would you want them to go to? And actually write down the maths that's involved if you could. Where do you think you'd like them to start?
Calling them X and Y.
Well, calling them X and Y is sometimes not the natural place for students. So what sort of things would you expect they would draw? But where would they start? Okay, give me an example. Right, so let's say if they start with side length of 1, what's this length? This is 6. Then what's the area? 6. So if I start to gather the values up, side length of 1 gives area of 6. Right, what about side length of 2? That's going to be 5, so area is 10. That's 2 and 10. Side length 3, right, let's say it's, I'm just drawing these roughly now, 3 by 4. So area is 12. 4? You've that done. 4 is the same as 3. 5 is the same as 2. 6 is the same as 1. Could you have a side length of 7? No. If you force the side length of 7, what area would you have? 0. Could you have a side length of 0? You won't have any area. It's a waste of time discussing numbers bigger than 7 and less than minus, or less than 0, isn't it? Negative integers. Now think about if we just stop there for a second and compare that to the exam question that was up there. Can you see I'm almost naturally at the domain between 0 and 7? Without giving the domain, just through drawing basic rectangles, I'm at the domain. Also, I think it would be important to stress to them here, what's the relationship between those two sides always? They have to add to 7. That's half the perimeter, isn't it? They'll have to give me 7. Okay. The issue then, how does algebra come in as the problem solver? Why do we need algebra? Exactly, like here you drew 3.5, did you? Or 4.5? Yeah, so you drew in between, was it, what did you say, 4.5 was it? Was one side? So you were finding a value in here. How many possible values are there in between? It's infinite. Where do you think the answer is? Somewhere in between 3 and 4. And if you had a Casio calculator, you could examine, looking at the table function, where it occurs. But there's infinite numbers that we didn't check. And that's where algebra comes in. This is the way to describe any of those infinite numbers. And from our discussion, what's this distance? 7 minus x. Those two have to add to 7. We saw that with the numerical cases. So what's the area of every possible rectangle with perimeter 14? 7x minus x squared. You could say that's mathematical modelling, where you build a model or a function to help you to solve a problem. So we've built this function now. It's equal to 7x minus x squared. Again, compare it to the exam question. Let f be a function. Like at third level, some people think that's the real mathematical skill, to build a function to help you to solve a problem in a situation. Now this is where we have to have a bit of a teaching discussion. How could I use that then to find the biggest garden? Right, so let's say you get a student graphing it, and you know yourself, that's when x is 3, and the output is 12. And similarly, when x is 4, the output is 12. But the in-between here is a free-for-all, isn't it? Depends on their graphing. I mean, you can have this stuff, or you know yourself, or even, join the dots, I'm still 6. So it is somewhere in there. How can I get to the right answer? Yeah, what do you mean, Joe?
I know what you mean. That still depends on the curve, doesn't it?
Well, you hit the nail on the head there, because you mentioned symmetry. Yeah, it's a quadratic function, so that's symmetric about an axis. And that axis is halfway between 3 and 4. How could I get the proper output? The graph may not give it to me. Back into this magic function, which is to help us. Any other way I could do it?
The average value between 3 and 4.
Use an integration. Still back at junior cert. You could maybe up at leaving cert. Either side. Yeah, you could, and you could use that table function to examine numbers either side, and you can see, yeah, it maximizes at 3.5 and the output is 12.25. But I'm more so thinking, is there any way we can manipulate a quadratic to help us to see where the magic is, where it maxes or minimizes? Right, how would you do that to complete the square on it? You can sketch it, can't you? You can sketch the geometry of it. Let's just do it algebraically with this one. If I take out minus 1, it's into x squared. See, I'm getting better. Usually I say there, take out a minus. So I'm taking out minus 1. Maybe I should write it. Into x squared minus 7x. Might be easier to complete the square. What's the technique? How do we do it? Take the coefficient of x, half it, and square it. And we saw in the last workshop, when you draw the geometry of that, it's lovely, because you can see it's physically completing a square. So we've minus 1 into x squared minus 7x. What's in here? Plus 3.5 squared, that's 12.25. And then what do you do immediately? Minus 12.25. Okay, if you tidy all that up, you get minus 1 into x minus 3.5 squared, minus 12 point, or plus, is it, yeah, minus 12.25. That's what that is, tidied. Bring in the minus 1, and we have this eventually. X minus 3.5 squared plus 12.25. That's called the vertex form of a quadratic, or the completed square form. It's the most useful form that you have, because you can see immediately where it turns, where it bottoms out or where it maxes out. Where is it? At 3.5, 12.25. And just to remind you, do you remember all that shifting and scaling stuff? Where we said y equals x squared is the mammy of all quadratics. So where is x minus 3.5 squared? Takes the parent function and brings it over here. Where's minus that? Inverts it. And what about plus 12.25? Moves the whole thing up 12.25 units. So you can see eventually it comes up here. And right up there is where the max occurs, and that's our 12.25. Of course calculus is the best, because look at all that work. If I just take a derivative, I get 7 minus 2x, and we know the derivative is 0 at the max. X is 3.5. Do you remember we said earlier you could revisit tasks? Like I could see somebody doing that at junior cert and later coming back to it at leaving cert to show that calculus is the most efficient way to find the maximum. But yeah. Yes. Yes, it's been in 2 sample papers already. So they are, and apparently to know a bit about this as well. Yeah. Well, that's the whole point. You complete the square anyway, so you can sketch and solve. No, higher level. And that's Tad Watanabe's point. It's about what we have and how we use it. As he said, it's how you use it that counts. Okay. So there's the end of the algebra. That's the end of what research suggests that we could do. We have one section to go. It's the circle. And it's the circle as a connecting device across the syllabus. First task I want you to do for me, talk to each other about where the circle appears in the syllabus. So how many places can you think of that involve a circle? Okay, and make a list. Right, so do you think the circle shows up much? Can you give me some places? Everywhere. It's in every strand. Area and volume of a circle, or area and volume section. Where else? Algebra. Line and circle. Okay. Statistics. Pie chart. Trigonometry, unit circle. Obviously the geometry of the circle, those theorems and constructions. Coordinate geometry of a circle. Calculus, finding where the equation of a tangent to a circle.
And you know, like the expand it with radiuses, increase with a ratio.
So related rates types questions. Yeah, very good. It's in complex numbers too, isn't it? Rotation through 90 degrees. I just took a look at the Leaving Cert ordinary level paper last summer, paper 2, just to see did the circle appear? Well, wait till you see this. You had a full question on coordinated geometry of the circle. You had a nasty enough little question about getting a shaded area. That's a tough question now, involving sectors and segments. You had to construct the incircle. there was a geometry cut that involved a circle and a semicircle, the right angle semicircle. Pie chart. This is all now in one exam paper. And the question on trigonometry at the end, you have to get the angle between two blades in this wind turbine and find the area of the disc traced out by a full rotation of the blades. And that's why in our formula and tables book we have area of a disc. They don't say area of a circle, that the circle encloses area. And you know, I think an important connection to make is, there's the area formula, isn't it, for a circle, pi r squared. Maybe we should think about it as a function. It's the a of r function. So you tell me what the radius is, then I'll tell you what the area is. And that's important in your related rates questions especially. So can you just go to your booklet a second? And if you just look at page 13, please, first. So starting on page 13, this is a fantastic resource. This is where one teacher has taken a look at the circle across Leave Insert and connected it up to as many places as she could. So largely what she's done is she's broken the circle down into 4 sections. The first part is the basics of a circle, so terminology associated, lengths, formulae and so on. Then she looks at where algebra meets the circle, and we call that coordinate geometry. The third part, she talks about the derivation of the equation of a circle, and then finally she gives emphasis to trigonometry and the unit circle. So there's a few big themes or points she makes throughout those pages, and I'll try and emphasize those as we go. So here's the first activity I want us to think about. And I'd like if you tried this, or if you've talked to someone about this. Here's Google Maps of the area that we're in now, and we're here. So this is Marshall House. And I want you to think about 3 different questions for me, if you could, in turn. Right? The first question is, how many circles is it possible to draw that contain where we are, Marshall House? So many circles is it possible to draw that contain this point? That's the first question. Okay, question 2. Last Friday there was a teacher here and she said, I'm never close to the Crescent Shopping Centre on a Friday. It's as if she was going to visit Mecca. So she was really on a high. So question 2 involves the Crescent Shopping Centre. How many circles is it possible to draw that contain where we are, Marshall House, and the Crescent Shopping Centre? And then the third question, if we bring in the regional hospital, how many circles is it possible to draw that contain all 3 points? And for each case there, I want you to tell each other why you've picked a particular answer. Okay, so many circles through 1 point, how many circles through 2, how many circles through 3. What's the most important thing about a circle? What defines a circle? Its radius and its centre. Okay, let's think about the first example we had here. So we'll take it that this is the education centre. And, no sorry, let me undo that. Here's the education centre, and that's the centre of some circle that it's on. So if I can see this. So that's a particular circle that contains the education centre. See, that's the language problem now. This is Marshall House here. Is it the only circle? Why not? You're not constrained by centre. And what about radius? So how many circles contain that point? Infinite. Okay, so just to show you, if I drag this remind you of anything? Down, 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 down. It's very like Bond, isn't it? So it's infinite circles, because there's no restriction on the centre or the radius. Okay? Now, next, what about the situation with 2 circles or 2 points? Joe, I heard you discussing that there, so what did you say?
Infinite number of points of circles.
Okay. tell me about restrictions. If I say that's the centre point E, is it restricted?
It has to be an equal distance from both points.
Right, and that's the radius, isn't it?
Yeah.
So you can see it must be equidistant from, you can see that? So it's equidistant from our points. But what about its location? It can be? Yeah, it can be anywhere, but it's restricted in one sense. Yeah, it's along a line. Which line is it? The perpendicular bisector of that chord, isn't it? So just to show you, here's our chord. There's the perpendicular bisector. This point E can move, but it is restricted to moving along that particular line. How many circles are possible? It's infinite, isn't it? It's a different type of infinity to the first one, but we are not going to go there. Okay, Cantor, the mathematician, went insane because of different types of infinity, but it's not as infinite, if you like, as the first one. Okay, we'll just leave it at that. Now, next, what about 3 points? There's only one. Why is that?
The bisector of the chord, the bisector takes at 1 point. So
Okay, let me take, here's a chord. That's the perpendicular bisector. Take another chord. Here's the chord between F and G. That's a perpendicular bisector. So they just meet at 1 point, which is our centre, isn't it? Okay, even if you took the third chord between those two, I think that's the perpendicular bisector. So your centre is fixed. What about your radius? Is it?
centre's fixed, your radius is fixed.
If your centre is fixed and those 3, hospital, shopping centre and here, are fixed, then your radius is fixed. So radius in each case must be the same. What are we really talking about here? That's the circumcircle. That's construction of the circumcircle. And just another idea that this teacher mentions in that document, the beauty of GeoGebra is you can just turn on the axes. So in a sense, in one click there, you're going from Euclid to Descartes. And sometimes it's a good idea to take constructions that you've done in the pure geometric plane and prove that they're correct using coordinated geometry. So the point of that activity really there is how important the centre and the radius are for a particular circle. Like you could say lots of even cert questions, the difficult ones are really about finding, well, where's the centre of the circle? You know, that's usually what the problem is. So if I just go back to what we were talking about, and I want to ask you about this. You know, this type of question here. Given 3 points on a circle, and you're asked to get the equation of it. Standard method that people use in the students use in the exam is an algebraic one. So it's where the students sub into formulas, build simultaneous equations and solve them. And this teacher that wrote the circle connections document thinks, you know what, maybe we should rely a little bit more on geometry than algebra all the time. Because this is like, do you remember the dog, rabbit and cat question? You can build equations and solve them blindly without really learning much or thinking about what's going on. So imagine taking the same question, 3 points on a circle, and we try and solve it geometrically. So could I do this with junior cert maths? How? Midpoint of? Okay, so here's... Well, yeah, that's the problem. If I join those two, it may not be a diameter.
You bisect the 2 chords, you get the same.
Yeah, so what's the maths there? For example, there's a bisector of a chord. How do I get the equation of that line? It's perpendicular, so we can get the slope, invert, change sign, and midpoint. And there's another perpendicular bisector, and they meet at the centre. So how will I find the centre? Simultaneous equations. And this teacher contends, and I would agree with her, if students do it this way, they're probably gaining more from a problem-solving perspective. You know, reasoning their way through steps to take and using geometry as opposed to blindly using algebra. Like one of the most common questions on Leaving Cert has been this one. They give you a line through the centre and they give you 2 points. Like that's almost the work halved, isn't it, in the geometry approach? Because you could take this chord, there's the perpendicular to it, get the equation of it just like you outlined there with junior cert methods, and there's the line given in the question. So you have half the work done and find out where they meet. So one of the next things she does then, and this is where I want you to chat again if you could, she talks about how to derive the equation of a circle. So I think this is page 19 in your tables. Could you tell the people around you how you teach that to students? X minus h to be squared plus y minus k to be squared is r squared. How many people start with the circle at the centre? Sorry, centre at the origin. Yeah? And then work it out, or work towards this one. Researchers say we should do it the other way. To start here, and then go back to the one that's centred at the origin. Can I just show you before, and feel free to add in here whatever you like. I just want to show you something I saw a teacher do once, and I thought it was so simple. Like most brilliant things, there was simplicity to it. She just went into class, and you have to take off your teacher hat now, okay? Pretend you don't know anything about the topic or what we're doing here. Because usually circle chapters begin fairly quickly with this, don't they? They get this in fairly fast. So this teacher goes into class and says to the class, here's a point A. What are the coordinates of A? 2, 3. Okay. Can you give me a point that's 5 units away from A? And I'll help you. I'll just put in the grid if that helps. Right, let's try that. 8, 3. Okay. Now I'm deliberately leaving that there, even though that's 6 units away. That's fine. But I'm going to use it. So can you give me a point that's 5 units away? 7, 3. Okay, another one. 2, 8. Good. Another one. 2 minus 2. You're really picking the easy ones, aren't you? Can you give me another one? Right, minus 3, 2. Okay. Now it's going to get a bit harder. So can you give me a point that's 5 units from A? What's it? 5, 7? Now what if there's students in the class and they're not sure where that came from? Like how do you know that that's 5 units away? It's in a diagonal direction. Okay, and all I'm doing in GeoGebra here now is just enabling the buttons. Look, so I'm just clicking on line segment and I can say, right, I'm trying to decide, is that 5 units away? So what I'll do is I'll create a right angle triangle to here and then up to here. So how could I check if it's 5 away? Well, this distance is 3 and this distance is 4. And if I apply Pythagoras' theorem, the distance from G to A is 5, isn't it? Right, now that's a big hint. Can you give me any other point 5 units away? 6, 6. Okay. What about over around here? Right, you could try symmetry, very good. Minus 1, 7. Okay. Any point down in this corner? Try it, so minus 1, minus 1. And then over here. 5 minus 1. Now you know yourself in class, someone's going to say, sure, they're all just on a circle. And that is not your definition of a circle. So locus of points that are equidistant from a fixed point. Lovely thing with GeoGebra though is I can enable the circle tool, define where the centre is, and stretch it to one of those points and show that it captures all of them, except for Morade's first one. And you know, that's no harm either. Why isn't B on the circle? It doesn't satisfy Pythagoras' theorem. Or you can see its distance to the centre is more than 5. How do you get to the general case then? Because what this teacher did in class was, she said the centre is 2, 3. The radius is 5. And she used the general case here, which is the algebra coming in again. So if this is the point xy, can you tell me what that distance is? That's x take 2. Notice it's 90. This distance? This is y take away 3. And if I apply Pythagoras' theorem, then x take 2 squared plus y take 3 squared must be equal to 5 squared. And she almost explained the equation as a condition that the points had to satisfy. You know, and I like that. If the point is going to be on this particular circle, then it must satisfy Pythagoras' theorem. Like lots of things in geometry, it's Pythagoras in disguise again. So how do I go from that then to the general case? Call the centre HK. And of course then, look with GeoGebra, just come over and turn off those axes. So we're not talking about specific numbers here. So if I call the centre HK, and this is any point on it, xy, then this distance similarly must be x minus h. Now I'm microwaving this because I know that in class you might have to tease it out a bit more. This is y minus k, and that's called a radius. So if that point xy is to be on any circle centred hk, then Pythagoras' theorem must be satisfied. And we get this, the general equation of a circle. Why is it easy then to go from that back to circles that are centred at the origin? Because it's just a special case of this, isn't it, where h and k are both 0. Now I realise that you're exhausted. So we're practically there. The last thing we're going to do in the room is have a competition. You are against the people at your table. There is a world championship. I'm not making this up. It's on in Vegas every year. If you find you're unnaturally good at this type of work, you can enter. Okay? Will you all go to page 9, please? On page 9, you'll see a blank page. No cheating now here, okay? On page 9, I want you to do this. Draw your best attempt, taking up about half the page, at a freehand circle. Okay, and what I want you to do is, tell me first, how could I use geometry? How could I use geometry to decide whose circle is the best? Well, I don't know where the centre is. It's the first thing.
You can do 3 points.
Yeah.
Make a triangle and do the circumcenter
Of
times.
that triangle.
Yeah.
Okay.
And do one bottom side and
And see, right, you'll still be making a call on it, won't you? Because you're trying to decide, does it fit properly on it or not?
Yeah.
Do you remember this result we saw a few minutes ago? The perpendicular bisector of the chord. Okay, imagine you took 3 chords. And let's say we take, so it's easy enough to see. If I took another chord here, and I took the perpendicular bisector, they won't meet, because your circle isn't perfect. What you'll find is they create a triangle at the centre. And who's the winner? Whoever's triangle is the smallest. So that's round 1, and that's what I want you to do first. Here's round 2. So I'll take it that you've decided who the winner of the first round is. Round 2, on page 10, will you try it again? Draw a circle for me, and we'll discuss a different method to decide. If this is the second circle that you draw, this time I'm going to put the result up. And I want you to tell me, firstly, what's the geometry? So I'm not involved in the centre in any of these. I don't know where the centre is.
Opposite angles at 280.
Opposite angles add to 180. When you do the activity, they won't add to 180, because you won't have drawn a perfect circle. So if you note these two, they add to 176. How many degrees am I away from where I should be? 4. I'm 4 degrees out. I don't even have to measure the other two, because if they're 176, then these two must be 184, because it's a quadrilateral. So you're 4 degrees out anyway in the other direction. So your second test is draw a cyclic quadrilateral, measure 2 angles with the protractors, and see who's closest to 180. Right, is it? Okay, 1-1 at this table, so we need one more, and here's the last thing, okay? Whoever designed this should get a medal for it. It's so clever. What's the geometry result that I'm thinking about here? Angles that stand on the same arc should be the same. They won't be, because your circle isn't perfect. The other issue we have with this method is I don't know what they should be. Let's pretend I measure them and I get 41, 43 and 46. What would be a good guess? If I don't know what it should be, what would be a good guess around what it could be? So use the mean. So I could get the mean. And how could I find out how far I am away from the mean? Get the standard deviation. So if you do with those 3, and notice I put that one down there a bit away from those, because by chance you could get 3 in the same arc. Get the standard deviation, and who's the winner? Whoever standard deviation is the smallest. So you're connecting it to your statistics. Okay, have a go at that. So one last time, draw a circle. And I'll show you on the calculator how to do standard deviation if you're stuck. Right, just in case you need it, how to do standard deviation on your calculator. Statistics itself on your calculator is in 2 places. One is where I press the mode button, and you'll see I get stat as part of the menu. Also, if you look above, see above the button with 1 on it, you see stat. Yeah. And it's important that students understand the difference as well. The button at the top is to put data into your calculator. Above number 1 is where you analyze data. So I'll show you what I mean. If I press mode and I press 2 for stat, you get this sub-menu here. At Leave Insert you'll only ever be worried about 1 or 2, and you'll only use 2 for correlation, bivariate. So we've only got 1 univariate data here. So if I press 1, you get this table. Could somebody give me their angles?
53, 53 and 54.
Wow, okay, so 53, I enter that, I press equals. 53, press equals, and 54. Just make sure you press equals after the last one. It's the only place sometimes you see people, or that you see people forgetting what to do. So that's the data entered, right? So then you press all clear. Clear your data. And then press Shift and 1. And you'll see here's the sub-menu for statistics. We're looking at standard deviation. That's involved in the variance menu, which is number 4. And then you can see sigma is number 3. So your standard deviation there, 0.47 of a degree. That's one really good circle. Is it yours or Anya's? It's your own, well done. That's 0.47 degrees. So whoever there among the pair has got the lowest, then you're the winner. So we're done. I have two hopes at the end. I hope you feel more tired than I do. That's the way students should leave the class. And number two, I hope that you got something at least that you could think about or use back in the classroom. And here are the codes for our survey, and we'll take those now. And if we could just finish the filming, I will be relieved.